Hello, my name is Clifford Collins and I'm a sixth-year medical student, and this is a lecture on medical chemistry, specifically for the first-year medical students of the University of Debrecen. This lecture is step 2. There are 5 steps. The first step is called in 4 minutes or less. It's a video just to show you basically the outline of the topic. The second lecture, this lecture, step 2, is called the basics of. So this lecture is going to be called the basics of atomic structure and periodic table. It's supposed to tell you the basics, just the basic information. And the next lecture is called everything you need to know about atomic structure and periodic table. It's going to be every detail, every possible detail that could be asked in the exam, every possible important detail that you need to know about atomic structure and periodic table. The fourth lecture is going to be called So You Think You Know Chemistry. So it's going to be a lecture about solving questions. So I'm going to have a lot of questions and we're going to practice it together. And the fifth lecture is going to be called Chemistry and Chill. In this lecture, it's going to be a live video and you can submit your questions and we will solve it live, and also we'll discuss the implications of the topic we're talking about, the clinical situations that relate to the topic. Okay, so in this medical chemistry course, we are going to be using this textbook, McMurray and Fay, and we're also going to be using the lecture slides as our source of information. I cannot show you the lecture slides because they are copyrighted, but I'm going to be using it. I have my phone here with the lecture slides, and I'm going to be using it. Every 25 minutes, I'm going to take a break. We are going to take a break for 5 minutes, just so that you can relax and you'll have your full attention. Yeah, so that's it. So let us start atomic structure and the periodic table. I'm going to be using the lecture slides to make sure I'm saying every important information. This is my first time. I'm sorry. Okay. So the first thing we're going to talk about, first I'm going to write the outline of what we're going to talk about. We are going to talk about the history and the models of the atomic structure. So we are going to talk about all the different models and the experiments that were used. Then we are going to talk about the atomic spectra, also called the line spectra. Yeah. Then we are going to talk about the quantum mechanical model. Of the atom. Then we're going to talk about electronic configuration. And periodic table or periodicity. I'm going to try to go slow so that you can understand everything. If the lecture is too slow, you can always increase the speed. Yeah. And I'm going to try to explain any difficult word that I use in the lecture just to make sure that you really understand what I'm trying to say. Okay, so let's start with the history and the models of the atomic structure. Okay, so the first real person that talked about the structure of the atom was Democritus and other philosophers also. Democritus existed before Dalton. He thought that the atom was indestructible. So you cannot destroy it and it's indivisible. So it's the smallest thing, cannot be divided further. That's what indivisible means. So according to Democritus, if you have a piece of matter, like a stone, and you break it down into two, and you keep breaking it down, keep breaking it down, you get to a small piece that cannot be broken down further. That small piece of matter is called the atom. Okay, so the next model was Dalton. Dalton gave the Dalton's theory. And in the Dalton's theory, basically the Dalton's theory was a theory, a model from the collection of the scientific knowledge at that time. So his model of the atom was similar to that of Democritus. He said that the atom is the atom is an indestructible, indivisible hard sphere. So indivisible, they're indivisible. And he also thought that the atom was the smallest part of matter. So there's nothing smaller than an atom. So according to Dalton, he described the atom using masses. So he described chemical reactions as rearrangement of masses, basically. So he described, so it's important to remember that he described chemical reactions. So according to Dalton, chemical reactions were not overlap of orbitals like we know it, they were just rearrangement of atoms. Okay, so the next theory that was given about the model of the atom was given by J.J. Thomson. J.J. Thomson, he made an experiment, the cathode ray experiment. And in this experiment, he discovered the electrons. And then he discovered that the mass of the electron was smaller than the mass of the atom. So if the mass of the electrons that he discovered was smaller than the mass of the atom, it means that the electron was smaller than the atom. That means the electron was a part of the atom. So that means the atom is no longer the smallest thing. At least the atom could be broken down into electrons. So he disproved Dalton's model, the Dalton's theory, and he gave forth his own theory. He made his own theory. His theory was called the plum pudding model. Because he thought that the atom was round, containing electrons, and the rest of the atom was just positively charged because the electrons he discovered were negatively charged. So it looks like a plum pudding. The plum pudding is a food, so plum pudding model. So that was the Thomson's model. The next model was given by Ernest Rutherford. Rutherford also made an experiment. He made the gold foil experiment. And in this experiment, he discovered the nucleus. We're going to talk about the details of each of these experiments in step 3. This lecture is just supposed to show you the basics. So Rutherford discovered the nucleus in his gold foil experiment. And so he was able to give his own model. His model was called the planetary model. So in Rutherford's planetary model, this is the nucleus, and you have electrons going around it. So it's called the planetary model because it looks like a sun and it looks like a star with planets around it. So that's why he called it planetary model. So you have negatively charged electrons moving around a positive center. So this is a positive center. Okay, so the next model was given by Neil Bohr. And that's Bohr's model. Bohr did not make any experiments. So no experiments. Bohr's model was because it was trying to explain certain things that Rutherford model was not able to explain. So for example, in Rutherford's model, there was a problem with it because here you have a charged particle moving in a circle. So we know from physics that when a particle is moving in a circle, it's changing direction constantly because you're not moving in a straight line. You're changing direction constantly. Okay, so if you're changing direction and you're moving, that means you're having acceleration. Acceleration is a change in velocity. Yeah, so you're having acceleration because your velocity is changing. Your velocity has a particular displacement, a particular direction. So you're changing direction, you're having acceleration. In this case, you're having circular acceleration. So there is a law in physics that says that when a charged particle is accelerating or decelerating, it gives off radiation. It gives out radiation. So according to Rutherford's model, if it were correct, you're supposed to have the nucleus and the electron moving and it's giving off radiation. And it's supposed to be losing energy and spiraling. And then it will collapse into the nucleus. So Rutherford's model was not stable. So Bohr was able to explain the stability of the atom. So how did he do that? He didn't make any experiments. He just gave certain statements that were to explain something. So they were called Bohr's postulates. Okay, so according to Bohr's postulates, the electron do not lose energy. So electrons do not lose energy while in the circular orbit. So he said the energy is fixed. So this gave rise to energy levels. So basically, you have one shell, two shells, according to Bohr's model, and the electrons here, they have constant energy. So this way he was able to explain the stability of the atom. Another thing that Bohr's model was able to explain was that it was able to explain line spectra. We're going to talk about line spectra later when we talk about all of the other models. The next model that we're going to talk about is the current model. It was given by Erwin Schrödinger and it's called the quantum mechanical model. Of the atom. Erwin Schrödinger, he used a different approach to describe the atomic structure. He did not just treat the electrons as a particle. He treated the electrons also as a wave, using the concept of wave-particle duality. So used wave-particle duality to explain electrons. Okay, so before we talk about this model, we have to talk about the wave-particle duality theory. So according to the wave-particle duality theory, it says that everything behaves both as a wave and as a particle. So basically, an electron can be explained as a wave and as a particle. So electrons and other particles behave So what does that mean? It means that if you have an electron, you can see the electron as a particle. This is the electron as a particle. Or you can see the electron as a wave. This is the electron as a wave. The real behavior of the atom, the real structure of the real behavior of the electron, the real structure of the electron is somewhere in between. So you can use, as a wave, you can use certain things to describe a wave. You can use frequency to describe a wave. You can use velocity, wavelength. As a particle, you can use things like position, mass, to describe it as a particle. So, yeah, as a wave, you cannot say a wave has a position. It's not really possible for a wave to have a position. But as a particle, you can say a particle has a position. But because the real electron behaves both as a wave and as a particle, it cannot really have a fixed position. So instead of having a fixed position, so no fixed position, instead, you see the electron has a region where there is a probability of finding the electron. And this region is called the orbital. So I'm going to write it again. Erwin Schrödinger, using his quantum mechanical model of the atom, he postulated, so he said that electrons, there's a region where there's a probability of finding the electron. So the electron is not just a particle where you can have a fixed position on a circle. which is like Bohr gave, called the energy level. But instead it has a region where there's a probability you can find the electron, and this region is called the orbital. We're going to take a 5 minutes break. Okay, so we're back. Yes, sorry about the abrupt pausation of the class. Okay, so according to Erwin Schrödinger, using the quantum mechanics model, we have orbitals as a region where there's a probability of finding an electron. So that means every electron stays in an orbital. So the orbital is like a house for the electron. And we can describe the orbitals using certain numbers called quantum numbers. So quantum numbers are numbers that can be used to describe the orbitals of an atom. So we have four quantum numbers. We have the principal quantum number, we have the orbital shape quantum number, we have the magnetic quantum number, and we have the spin quantum number. Okay, so out of these four quantum numbers, the first three describes the orbital. The orbital is the region where there's a probability of finding the electron. So it describes the orbital. This describes the electron specifically. So what the quantum numbers do not describe is the atom. They describe the orbital or the electron, not the atom. So in questions, when they're asking you to write the quantum number of something, they're usually asking about the electron or the last electron in the atom. They're not just going to ask you to write the quantum numbers of the entire atom. It's usually about the electron. Okay. So now that we have talked about the quantum mechanics model, we are going to focus on the quantum numbers now. Okay, let's start with the principal quantum number. The principal quantum number is written as n. So what does it describe? It describes the energy level of the orbitals, right? So basically, if you have the nucleus, you have different shells. These are shells or energy levels. So this is described by the principal quantum number. Given as n. So this is n equals to 1. This is n equal to 2. So there are different values for n. The values for n ranges from 1, 2, 3 to infinity. So n is equal to a positive integer. Okay, the next is the orbital shape quantum number. And this is written as L. So this describes the shape of the orbital. Okay, so we have different shapes, different types of orbitals. We have the s orbital, we have the p orbital, we have the d orbital, we have the f orbital, we have the g orbital, and from here it goes alphabetically. So after G is H, G, H, A, B, C, D, E, F, G, H, I, J, alphabetically. It goes okay, let me not embarrass myself and spell alphabetically wrong. Okay, so this one is s orbital. The number for L is given as 0. When is p orbital, the number for p is given as 1. When is d orbital is given as 2. And is L, you understand, 3, 4, 5. Okay, so if you have an atom, if you have an energy level n is equal to 1, so the first energy level has only one orbital, So you only have, that's why you have only one s2 when you write the electronic configuration. We're going to talk about the electronic configuration later. So n equal to 1 has only one orbital. The second energy level has how many orbitals? You have one s2, then you have 2s2, 2p6. When n is equal to 2, n has 2 orbitals. So that means the second energy level has 2 orbitals. It has the s orbital and it has the p orbital. So when n is equal to 3, it has 3 orbitals. Okay, so you can see how it works. So when n is equal to 1, it has only the s orbital. So that means the value of n equal to 1 has L equal to just 0. So when n is equal to 1, the value of L is 0 because it has only s orbital, and we know from here that L is equal to 0 when it has s orbital. But when n is equal to 2, so second energy level, it has 2 orbitals. So you have 2 values of L. You have L is equal to 0 because you have the s orbital. Sorry, you have this s orbital here. You have this s orbital. And then you have L equal to 1 because you have this p orbital. So that means for the second energy level, you have 2 values of L, 0 and 1. So you say L is equal to 0 or 1. When n is equal to 3, you have 3 orbitals. So you have your 3s, you have your 3p, and you have your 3d. So you have different values. L is equal to 0 for your s orbital, equal to 1 for your p orbital, and equal to 2 for your d orbital. Don't forget L is equal to 2 for your d orbital. So your values of L is 0, 1, and 2 when n is equal to 3. That means for your third energy level, your values of L is 0, 1, and 2. So we can see here there's a pattern. So the possible values of L ranges from 0 up to n minus 1. So that means if your n is equal to 10, the possible L orbitals you're going to have, the possible values of L you're going to have is 0, you're going to have 1, you're going to have 2, you're going to have 3, 4, 5, 6, 7, 8, up to 9. So that's what it means. Okay, so the next stuff we're going to talk about is so the next quantum number we're going to talk about is the magnetic quantum number. And it's given as ml. So the magnetic quantum number describes the orientation of the orbital. So for example, if you have an orbital, say s orbital is a sphere, and we know spheres, they do not have a particular direction. They're basically in all directions. So you can say it has no orientation, but just one. The next is your p orbital. P orbital has a dumbbell shape. So the orientation is the direction that this is facing. So your p orbitals, you can have three different orientations. It can be facing the z-axis, it can be facing the x-axis, or it can be facing the y-axis. So you're going to have your pz, px, and your py. So you have three possible orientations. So there is a kind of pattern to it. Okay. In your s orbital, previously we learned that for s orbital, the L that describes the shape of the orbital is given as 0. So your value of ml for your s orbital is just one particular orientation. So this one orientation is called the 0. So you have only one value of ml for s orbital. 0 is a value, don't forget, 0 is a value. 0 does not really mean 0. In this case here, for your p orbital, we know from our p orbital the L is 1. So you have three different values of your p orbital, your pz, your px, py. So your px, py, and your pz. So you have three of them. So that means you're going to have three values of ml. This is given as -1, this is given as 0, this is given as +1. So you have three values of ml for your p orbital. So the number of values of ml that you're going to have for every L is given as ml is equal to -L ranging to +L. So for p orbital, your ml is given as -1 because your L for your p orbital is equal to 1. 0, you have to include 0 and +L. For your s orbital, your ml is just 0 because minus 0 to plus 0 is still 0, so it doesn't count. How about for something else? Let's say for a d orbital. Our d orbital, our L is equal to 2, so our values of ml is going to be minus 2, minus 1, 0, plus 1, and plus 2. So we have 5 values of ml. So that means we have 5 orientations of the d orbital. Okay. The next quantum number we are going to talk about is the spin quantum number. So remember, we said our spin quantum number describes the electron, not the orbital. So this spin, it describes the direction of the spin of the electron. So from this, if you're talking about spin of the electron, that means we know that our electron is not just stationary. It doesn't just stay. It doesn't just stand. It spins in a particular direction. It can spin this direction, or it can spin this direction. So it can be clockwise or anti-clockwise. The clockwise just means in the direction of the clock. So you know your clock goes this direction, 12 to 6. So this is clockwise. Okay, so when it spins in the clockwise direction, we say the value of the spin quantum number is given as plus half. When it spins in the anti-clockwise direction, it's given as minus half. So there are just two possible values of your spin quantum number, plus half and minus half. That's just it. Your spin quantum number does not depend on the other quantum numbers. And we said it does not describe the orbital. It describes the electron. Okay, that's your spin quantum number. So we have finished talking about all of the quantum numbers. Now we are going to talk about the electron configuration. Okay, what is electronic configuration? Electronic configuration is the arrangement of the orbitals in an atom. So it is the arrangement in order of increasing energies. What this means is that the orbital 1s with smallest energy is going to be written first, followed by 2s, then 2p, and then 3s, and then 3p, and it continues for s, 3d, and blah 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 blah. It continues. So the electronic configuration shows how the electrons fill up the orbitals. So if you have just one electron, the first electron goes here. So it shows how the electrons fill up the orbitals in the atom. And the electrons fill up the orbital in a pattern that follows the Aufbau principle. So the Alpha principle is basically a collection of three other rules. The first is the lowest energy principle. Second is the Ohm's rule. And the third is the Pauli exclusion principle. Okay, let's talk about these three rules. The lowest energy principle basically says that when you're filling the electrons in an orbital, you fill the orbitals with the lowest energy first. So the lowest energy orbital gets filled first. That's just it. So if we have your let's say you have carbon. Carbon has 6 electrons. So you're going to fill in the 1s first, followed by your 2s. Because your 1s has lower energy compared to your 2s, and your 2s has lower energy compared to your 2p. And then this. Okay, why did I yeah. So when you're filling the electrons, you can show it in terms of arrows. One arrow is pointing up and one arrow is pointing down. We're going to explain why one arrow has to point up and one arrow has to point down later. Okay, next is the Ohm's rule. Okay, for the Ohm's rule, we can also use this carbon to explain it. When you fill this and this, this and this, according to the Ohm's rule, you cannot put the next two electrons here. It says the Ohm's rule says that when you're filling orbitals with the same energy, you have to fill them singly before you pair it up. So orbitals with the same energy. Orbitals with the same energy are called degenerate orbitals. So are filled singly before being paired up. So according to the Ohm's rule, this is wrong. So you have to fill it this way. Because here you have your px and your py. These two orbitals, they have equal energy. So you have to fill them singly before you can pair it up. So let's say we are dealing with something like sulfur. Now let's use something smaller, oxygen. Oxygen has 8 electrons. So you fill your this. You've used 4 electrons so far. So you have 4 more electrons. You have to fill them singly before you pair it up. So this is how it works when you're writing the electronic configuration. Like when you're drawing the electronic configuration. Okay, so there's also another part of the Ohm's rule. It says that when you're filling the orbitals, they have to have the same spin first when you film them singly. So for example, for this carbon here, carbon has 6. So 1, 2, 3, 4. If you put this up and then this down, this this when you film them singly here, they need to have the same spin. So this is a violation of the Hund's rule. So you have to do it this way. The two electrons need to have the same spin. You cannot have them different spin when they are being filled singly the first time around. They must have the same spin. Usually we put them up to signify the plus half instead of down. Okay, so that is the Hund's rule. We're going to talk more about it in step 2 and step 4. Okay, the next energy level we're going to talk about is the next rule we're going to talk about is the Pauli exclusion principle. This says that no two electrons in an atom can have the same 4 quantum numbers. I'm going to write it here. No two electrons in an atom can have the same 4 quantum numbers. So what does that mean? It means that if you have let's use oxygen. If you have oxygen, oxygen has 8 electrons. You have your 2 here, you have your 2 here, and then you have this. If you're going to pair up this here, you cannot also make it go up, because if this is up and this is up here, they are both having the same spin. So that means for this electron, it has 2px, right? 2px, this is 2py, 2pz. It has 2. This 2 signifies the principal quantum number. So n is equal to 2 for this electron. And p means L is equal to 1. Because L is what? The orbital shape quantum number. Since it's p, L is equal to 1. And then the orientation. We know that the values of ml when L is equal to 1 ranges from -1, 0, and +1. So this px is going to be -1, py is going to be 0, this pz is going to be +1. So our ml here for this is going to be, our ml for px is going to be -1. And then our mx is going to be, since it's up, we say up is +half. But now this electron has exactly the same thing here. So it's going to have the same n, it's going to have the same L, it's going to have the same ml, and it's going to have exactly the same mx because it's pointing upwards. So this is a violation of your Pauli exclusion principle. So because of the Pauli exclusion principle, when you're pairing up electrons, one of them must be up and one of them must be down, so that they cannot have the same spin, because they're already sharing the same orbital. That means they're already sharing the same n, the same L, and the same ml, so they cannot have the same spin. So if one is up, one has to be down because that's the only way you can obey the Pauli exclusion principle. So this is a violation of the Pauli exclusion principle. Okay, so the next thing we're going to talk about is we're going to talk more about the electronic configuration in step 3. We're just going to briefly talk about the periodic table. So what is the periodic table? The periodic table is a table that shows the arrangement of elements based on increasing atomic number. So in the periodic table, you have in the periodic table, this is a periodic table. You have this vertical row that are called groups. Sorry, these are columns in English. So the columns represent the groups, and the rows, the horizontal rows, represent the period. Okay, so you have to fill in the periodic table in order of increasing atomic number. So that's just how it works. So the first element here is hydrogen because hydrogen has atomic number of 1. Second element here is helium because helium has atomic number of 2. And it goes in that order. It goes in that order, increasing atomic number. So when you fill in the in the elements according to increasing atomic number, we can see trends of particular chemical properties. So this trend of chemical properties such as the atomic radius or the ionization energy or the electron affinity or things like that. This trend is called periodicity. So we're going to talk more about it now. Periodicity is a trend of chemical properties in the periodic table. A trend means pattern. So it means how the patterns are. So patterns. Okay, so the first trend that is important to talk about is the atomic radius. So let's talk about atomic radius quickly. In the periodic table, first, in the periodic table, atomic radius change in a specific way. First, what is atomic radius? Atomic radius is the distance between the nucleus and the outermost electron. So the distance between the nucleus and the outermost electron is called the atomic radius. So there's a particular trend of atomic radius in the periodic table. um, down the group, that means this direction, down the group here, the atomic radius increases. But across the period, across the period, the atomic radius decreases. This is simple because down the group, okay, let's talk about down the group. Down the group, we have more shells. You can see bigger shells. So for example, if you have hydrogen, hydrogen has just one shell. If you have lithium, lithium has two shells. If you have sodium, sodium has three shells. And they're all in group 1. So that means they're all here. Hydrogen, lithium, sodium. So because you're having more and more shells, the distance between the nucleus and the outermost electron is going to increase. So down the group, the number of shells increases. So the atomic radius increases. Okay, what about across the period? So across the period, yeah, we have the same number of shell between lithium, beryllium, boron. So we have exactly the same. We have exactly the same number of shells. But what we have is that lithium has atomic number of 3. Beryllium has atomic number of 4. Boron has atomic number of 5. Atomic number gives the number of the proton. So that means lithium in the nucleus has 3 protons. Beryllium has 4 protons. Boron has 5 protons. But they have exactly the same number of shell. So that means that since beryllium has 5 protons, the protons are positively charged. The protons are going to attract the electrons closer to the nucleus because there are more protons, so there are more total positive charge in the nucleus. So the proton is going to attract the electrons closer, and so you're going to have the outermost electrons will be closer. So as you go across the period, you're going to have more and more protons, but the same shell. So that means the shells will be closer and closer to the nucleus. So the atomic radius decreases. Nice. So we see across the period, the number of protons increases. As the number of protons increases, the total positive charge in the nucleus increases. And so the attraction between the proton and the outermost electron, this attraction is called a nuclear charge. It's going to increase. And this will cause the decrease in the atomic radius. Okay, we're going to talk more about this in step 3. Okay, so the next chemical property that we are going to talk about is the electron affinity. Now, we're going to talk about ionization energy. What is ionization energy? Ionization energy is the energy that is needed to remove an electron, to remove usually the outermost electron from the atom. So it is the energy needed to remove an outermost electron from an atom. Okay, so whenever we say energy needed, we're talking about positive energy. So you need to put in energy. Why do you need to put in energy? That's because there's an attraction between the nucleus and the electron. So because this attraction causes the electron to be stable and to go towards the nucleus, in order to break this attraction, to break this stability, you need to put in energy. So that means our ionization energy is always positive. Well, yeah, for neutral atoms, at least. Okay, so you need to break this energy now, break this attraction. Now let's discuss how does it change in the periodic table. When you're going down the group, you're having more and more shells. The distance between the nucleus and the outermost electron is increasing. So what does that mean? It means that the nucleus is far away from the outermost electron. So that means this attraction is weaker. So the energy required to break it is less. So that means down the group, the ionization energy is going to be reduced because you need less energy to break this attractive force. So that's what happens. Ionization energy decreases down the group. Because down the group, the number of shells increases. The outermost electron is farther from the nucleus and less energy is needed to overcome the attractive force. Okay. So that is why the ionization energy decreases down the group. What about across a period? Across a period, okay, across a period, yeah, the number of shell is the same, but the number of proton is increasing. So we have increasing nuclear charge, right? The number of protons is increasing. The attraction, the attraction between the protons and the electron is increasing as you go across the period. So the energy that is needed to break this attraction is going to be increasing. So that's why ionization energy increases across the period, because this attraction is increasing. So across the period, the ionization energy increases because the number of protons increases. So the nuclear charge increases. Remember, the nuclear charge is the attraction between the protons and the outermost electron. So the energy, okay, so that is why the ionization energy increases across the period. Okay, so the next we're supposed to talk about is the electron affinity. But the electron affinity does not follow a real trend. Does not follow a trend. The only thing you need to know about electron affinity is that here in this is group 7, this is group 8. The electron affinity is very negative for group 7 and very positive for group 8. First, let's define what electron affinity is. Electron affinity is the energy needed or the energy released when an electron is added to a neutral atom. So for group 7, since they have 7 electrons in the outermost shell, they are almost octets. So if you add one more electron, they're going to be very stable. And when something is very stable, when something becomes more stable, they release energy. So because they're going from less stable to more stable, they're going to release energy. So I'm going to show you here. Cl plus electron to give you this energy is the electron affinity. And this is going to be negative because you're releasing energy. That's because this is more stable, less stable. This is more stable because this has 7 outermost electron. This has 8 outermost electron. So this is octet. We're going to talk more about this in step 3. So we are going from less stable to more stable. You release energy. And so in this case here, the electron affinity is negative. But if you're going for group 8 here, the noble gases, and you're trying to add an electron to it, this is already octet, and this is not octet, because this has 8 outermost electron already. And now because you've added one more electron, this is not octet, it has just one outermost electron. Let's show it here. This already has 8 here. If you add one more here, now this is going to have 1 here. This has 8 here. So this is not octet. And this is stable, going to less stable. So if it's going from stable to less stable, you need to add energy. Because this is not a spontaneous process, you need to add energy. So this your electron affinity is going to be positive. So in our group 7 has the most negative electron affinity, and our group 8 has the most positive electron affinity. So that's the basic thing you need to know about electron affinity. Okay, so I think this is the basic stuff you need to know about this topic. I'm sorry I felt a bit anxious because this is my first time making a video about this. I'm probably going to um, edit this video, update it when I become more comfortable making online videos. I'm much more comfortable making face-to-face classes because I've had 3 years, more than 3 years experience teaching students one-on-one. But this is the first time I'm making a class without actually seeing a student. So forgive my anxiety. I'm going to get better. So if you have any question, please post it on the comments or send me an email with your questions. If you want to book a class, please send me an email. It's on my website and it's on my Facebook page and also on my YouTube page. Okay, see you next time. Step 3 on atomic structure and periodic table. Have a nice day.